The name of this video is Fermi Water. Let us consider an aluminum atom, or perhaps a copper atom. In a very simplistic model, such an atom is comprised of a nucleus. The nucleus is made of protons and therefore is positively charged. So we will sketch it in orange for positive charges. This is our positively charged nucleus. Characterized by a positive charge Qn, positive. Such an atom is also comprised of a cloud of electrons orbitating around the nucleus. A subset of these electrons, it's very closely located around the nucleus. This set of electrons, this cloud of electrons, is called kernel electrons. So let us sketch them in red, a dashed dot line, red and yellow. So all these electrons interact strongly with the nucleus, so they're very closely connected to the nucleus. Okay, so these electrons obviously are charged negatively, and we will call them kernel electrons. With a charge, negative charge, Qk for kernel, which is negative. Finally, the overall atom has to be uncharged in the neutral state, so we need a further cloud of loosely bound electrons, which are called the valence electrons, which we will finally sketch completely in red for negative charges, which orbitates further out around this structure in this system, and so this we will dash it. Great. So these are the valence electrons. Which are characterized by a negative charge, QB, smaller than 0. As I said, the whole system has to be in the neutral state. So let's sum up all the charges. So we have Qn, which is positive, the nucleus, protons. This has to be summed with the Qk, which is negative. And finally, with Qb, in such a way that this sum of positive and negative charges equals to 0. Okay, so it's custom to group together the protons, Qn, with charge Qn, and the kernel electrons. This summation, is this a positive or negative charge? Obviously, it's a positive charge because the protons is the whole set of protons inside the nucleus, whereas the kernel electrons is only a subset. The overall sum has to give us 0. So this quantity is clearly positively charged. And this positively charged quantity, we call it an ion. So an ion is positively charged. Okay. So we have an ion which is positively charged. This structure here, this is our ion, if you want. Okay, which is positively charged. and orbitating around it loosely bound, negatively charged valence electrons with charge QV. What happens when we take an Avogadro number that is a very large quantity, Na, of such atoms? When we do that, and we put them together to form a metallic object, like a block of copper, what happens is that all these valence electrons blend together to form a so-called Fermi sea of electrons, which is effectively like a gas of electrons. Okay. Why is that? If you know a little bit of chemistry, you know that this quantity, these valence electrons, are those that participate in all chemical reactions, for example. In general, are those participating in all interactions between one atom and another atom, or many atoms together, as in the case of an Avogadro number of atoms. So again, if we go back to the Avogadro number of atoms, in this case, we can sketch this metallic object as fixed ions, which I sketch in orange. Okay, so the fixed ions here, they form a lattice, typically a periodic structure. So for example, we will have a positive ion here, another positive ion here, one more here, etc., forming a sort of periodic structure. And of course, this, you should think about it in three dimensions. So these are all the fixed ions. They don't move. Well, of course, everything moves a little bit, but they are pretty much fixed around their center of charge. Okay? So they are fixed around their center of charge, and they're positively charged, okay, with this charge Qn plus Qk. The valence electrons blend together, so they blend, and they are free to move within these fixed ions. All right, so as it turns out, the valence electrons in this configuration where we have an Avogadro number of atoms, they are called conduction electrons. So we go from valence electrons to conduction electrons when we have many such atoms. And as it turns out, one of these negatively charged conduction electrons can move by several atomic distances. So this means that it can macroscopically move. So when it can move by many atomic units, we say that this electron can move macroscopically. Macro, not micro, but macroscopically. In one of the first videos of this course, we distinguish between conducting materials and insulating materials, where instead of having a macroscopic motion, we can only have a microscopic motion about the center of charge. We will consider these materials in 342. They generate, for example, dielectric materials. Here, we will only consider the case of conductors, where these electrons, which are also called charge-free carriers, as we will see in the case of currents, can move around macroscopically in this object. Now, what does keep the electrons within our metallic object? What is the container that keeps it? That's why I call this the Fermi water. So we have a water, actually it's more typically it's called like a gas, but for an example, let's call it as a water. We have a water liquid, okay, of electrons, which can move around this metallic object. What is the feature that keeps these electrons from going outside the metallic object. In order to understand that, we need to look at the interface. Suppose that here we have a vacuum. Okay, this is our boundary here. So this is the boundary of a metallic object. Okay, so at this boundary we have positive ions, the last set of ions which sits next to this boundary. And then we have a sort of a vapor of negative conduction electrons which orbitate around them. In this fashion. So around this boundary, we have effectively a positive boundary, and effectively the center of charge of this will be a negative boundary with a distance, let's call it small d. So the distance small d is an average distance between the last ions before the boundary of the surface of the metallic object, and then this vapor of electrons which sits here slightly on the right hand side. There is an average distance which we just call simply small d. This configuration is called the Helmholtz double layer, and in fact is nothing but a double layer of charges, which I told you to discuss in Piazza at some point in a previous video. So we have positive charge on this left layer, negative charges on this right layer. It's a model, okay? Of course, they move a little bit, but we can approximate it as such. So this is an electrostatic double layer, okay? And now the aim of the next video is to understand the physics of this electrostatic double layer and why this prevents all this water, this Fermi water, to go outside in the vacuum, and instead they remain within the metallic object. Before concluding this video, now that we know qualitatively that there is a double electrostatic layer which prevents this Fermi water to go outside the container, like a glass, what kind of interactions can we have within this metallic object? Well, it can happen that a negatively charged particle can interact with a positive ion. So there can be a collision of this type. There can be this type of collision. These are collisions. There can be a collision between negatively charged particles that encounter each other. For example, this negative particle can encounter this negative particle, and there can be a negative-negative collision. So there can be this kind of collision. So this is the second type. And the third type is between a negative particle here and this double layer, where eventually the negative particle will bounce back. So it's between the particle, a collision between the particle and the surface, the boundary of my metallic object. So we can have three types of interactions or collisions: ion, electron, 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 wall or surface. And as it turns out, all these collisions are all inelastic collisions. If one day you will take a course on solid state physics, you will see that there is the very first model, which was proposed in 1900 by Paul Drude, a German physicist, accounts only for interactions between the Fermi water of negative electrons and the positive ions. Then a few refinements also take into account for electron wall interactions. And these collisions, these interactions in this Drude model are inelastic. And this allows us already to show many properties of metallic objects. Then further refinement are called the Fermi free gas model and the Fermi nearly free gas model, which eventually leads to Bloch's theorem and Bloch's functions, which are based on the Floquet theorem for periodic structures, because remember that these ions, which are fixed, so that fixed ions, they form a periodic structure. This eventually you will see it in a solid state physics course. Okay, so to recap here, we started from a copper atom, which has a nucleus, kernel electrons, and valence electrons. The overall sum goes to 0. The valence electrons are those that participate in interactions with other atoms. If I take an Avogadro number and I put them together, the glue which puts them together is due to these valence electrons, which then become conduction electrons, free to move macroscopically, bouncing around a layer of positive ions, which are fixed in their center of charge. These negative particles, the conduction electrons, can interact with the positive ions with each other or the wall in inelastic collisions, that is, energy is not conserved. And finally, they are kept within the object, the metallic object, by a double layer, a Helmholtz double layer, which is an electrostatic layer. That's it.